thanks for the opportunity of this, but I think it's nice also that by the end of the day, you will be also an artist. You are participating icon, but today we'll tell you a little bit of art. And art is actually the essential part of the air system, which is atmospheric composition. And here we look at the aerosol and reactive tracers, which is basically aerosols and chemistry. How we organize this talk, I think I need to click now so that we proceed, but it doesn't really appear. I click here and, well, it doesn't move. It moves here, but not there. Yes, I'm trying, but bist du? Es geht forward nicht da. Ah! Oh. Welche Präsentation vorsitzen vielleicht da? Jetzt? No? No.
Einmal, was machen wir bitte einmal zu?
Sorry, Daniel. Okay. Yeah, so we're gonna give you a little bit of overview of the capabilities of icon art, and you will have some quick experiments. But you already saw in the icon part that it is much more to learn and to try. And so we have some documentation, website, and experiments that you can keep working on and more. We will talk about, after this overview, which is given by me and Stefan Versick, we will, after the break, talk about primary aerosols. Then after the lunch break, we will see a little bit of the air quality by the colleagues from EMPA. And then we will talk about the secondary aerosols and chemistry when everything comes together. So this is our team that you see. Four of us are here, and you will see them. And Dominic Brunner will be joining us online in the afternoon for the lecture on chemistry. And actually, I have to thank Stefan, Julia, and Corinna for preparation of everything. Things that work are their effort. Things that don't work are my fault. So this is, I think that they did a great job, and we will see it later on today. Okay. Let's talk about art. And art is actually the atmospheric composition part of the icon modeling framework. And why is the part of the icon modeling framework? Because it is in the repository. So when you check out the repository of the icon, you already have the art. You just need to configure it by enabling art, and then you can use it. So there is nothing hidden or non-open source about it. It benefits from all the features of the icon. It can be used in the fully coupled large eddy, numerical weather prediction and climate mode. And it's usable for from local to global, from limited area and nested configurations. And you can also tailor it to your specific applications. You will see 3 examples today, which are really tailored to specific questions. And this is what all the users can do. What is also kind of compared to other atmospheric composition models is a bit specific about art. It is used operationally at the DWD and Meteo Suisse. At the DWD for pollen forecasting, if you have anyone allergic in the family, you can Google pollen forecast of the DWD. It's by Icon Art. Not in the season, but a couple of months ago, it was a bit too much hay fever ongoing in Germany and most of Europe. And there is also dust forecast, which is also done by DWD. If you look at our website at the KIT, we can find the dust dashboard, which shows the daily forecast of dust. What I'm going to tell you is a little bit of how we do atmospheric composition modeling, and then how you can enable art within an icon simulation. And then what it actually does, or what happens during these processes, or this individual, or what kind of basic information or equations of that. Every atmospheric composition model is basically about solving this sort of mass balance equation. This is, you see, is, for instance, for a gas species that has a density of rho I here. And then you see all of the processes from the emission, transport, transformations through chemistry and microphysics, and the removal. And if you look at the transport processes like advection, mixing due to turbulence, and the convection, it is done on the icon side. So we basically pass the tracers to icon for the transport, and then we calculate on the art side basically chemistry and scavenging that you see in terms of transformations. And of course, we need emission to have in the model. So it could be mechanical emissions, online emissions like dumps or sea salt, which are delivered by wind and meteorology, and it could be also offline emissions, means like reading input files for anthropogenic emissions, for instance. And everything that goes up comes down. This is the principle, and comes down to through the position here that you see in this equation also. And this, in principle, is a box model that we just, in the Eulerian approach, we just put this equation at each grid box, and then the question is how the grid box looks like. We had previously the rectangular grids, and now in the icon wall we have the triangular icosahedral grid. And so basically the atmospheric composition models are box models. And this makes them kind of attractive also for machine learning, because this is an ideal world. You don't need to be too much worried about the dynamics. Well, it's not, it sounds easier than it is, but yeah, a kind of principal difference between those. If you look at the art code on the open source repository, you will see these folders, and on the other side of the slide, I'm showing you the coupling between icon and art. And in the folders, you will see aerosol dynamic processes like condensation, nucleation, coagulation, all the code parts about it. Then we have the chemistry, including initialization and processes. Then we continue by emissions, everything about emissions in this folder. Then we have some external and I/O. One important aspect of icon art is that it interacts with cloud and radiation. So this is the cool part of the online fully coupled models, that the icon can know about the aerosol fields and adopt accordingly. And this is a very important feature, because usually weather forecast models or climate models rely on climatology and not prognostic aerosols, or let's say varying aerosol fields.
Sorry, just to clarify, on this chart, this the selection of the places, does it mean, for example, that emissions are executed at dynamic time step?
Yes. Yeah, it's timing and a little bit also where you see also the orange boxes around icon processes. This means that we also exploit that process. For instance, in the turbulent diffusion is also the position parameterizations, and also coupling with microphysics and radiation. I was saying that this interaction with the radiation and cloud is a key parameter, and this was one of the main motivations of having icon art now running operationally by the DWD, because it enhances the, let's say, for instance, solar energy forecasting during the aerosol events, in this case, Saharan dust events. And just to have an idea how often this happens in year, in southern Germany, we have up to 50 days per year Saharan dust in the atmosphere. In northern Germany, where we are now, about 20 days. But in few days, really, it could be significant loss to the energy market. So it was really a good motivation to go in that direction. And in this run control example, you will find some examples of the run scripts and XML files that you need to run standard configurations. And then at the end, we have some shared modules and a little bit of tools. But now let's have a look and see what do we need for an icon art simulation. So everything that you need for icon, you need it also for icon art. So, and on top of that, which actually, that we need grid, external parameters, and initial conditions for the metrology. On top of that, what you need to enable art in the configuration and compile. And we have also an example, if you want to do the full chemistry, it's also GPL, enable art GPL. It's an additional option. We can find it in the documentation, but not here. Then you need to prepare the input data, which are the initial conditions for the chemical fields and aerosol fields. You can, of course, start from zero, cold start, and have a spin up, but it depends on your scope. Then you need also, depending on the setup, if you have a limited area, you need boundary conditions and of course, emission data. Then, adopt the JavaScript and use it for the submission. And we have a specific part in the icon name list that you all know now, and art NML in the art name list, and I will show you in a minute. And this is what I was talking about, enabling art. First, you need to go to the run NML of icon and put the L art. So you want to do art in icon, you have to put this through. And once you have it, then you have to specify in the art name list, art NML, what you want to do. And there we have generally three types of switches or options. One is the logical L art, which is basically for on and off of the processes. Let's see that, for instance, the example in this one, we turn on chemistry, we turn off chemistry and turn on aerosols. Sorry, Stefan. So we just do aerosols in this one. And then in the other one, the I art is more integer. So when we have several options of handling a certain process, like let's say the washout, we have, if you want to have the convective precipitation or not, and how do you do the calculations, you can choose the options. And then we have also the characters that basically guides the model to use the XML data. You will hear about the XMLs later on, what they do, but XMLs have basically the metadata that art needs to do what it should do. When it needs, for instance, to do aerosols, it needs the XML data to know how to deal with the aerosols, which tracers and which sizes are needed. There is also compatibility or combination aspect that has to be taken into account. For instance, when we put chemistry to true, we have to tell the model which kind of chemistry are we looking at. What you see in the last column, we have the chem tracer, for instance, here, one example, or mecha tracer. You will learn about it, more about it in a minute, in the part that Stefan will present on the chemistry. And each of these options, if you put the the chem tracer or mecha, then you have to provide certain XML files or metadata that the model knows what it should do. We have also here, you see the point source option that also needs the XML file. And for the aerosols, what you see there, we need 3 XMLs basically. We need modes, tracer, and the emission. So modes tells the model how many modes are we considering. I tell you in a minute. And then we have the aerosol species and the emission. So it tells which tracers are emitted to each mode. And this is the fun part about the aerosols. When we talk about the chemistry, we are only dealing with the composition. So it is molecules. When we talk about aerosols, they are particles. And this is one TEM image from aerosols, one sample or individual particles from sample containing millions of particles. And imagine that we have billions of particles suspended in the air around us. And you don't see 2 of them similar to each other. Figure. So if I want to break down this into modes of variability, I can tell you that we are dealing with chemical composition, size distribution, mixing state, and morphology. And this makes aerosol modeling fun. I don't want to say complicated, but fun. And For the chemical composition, we say, okay, how much is sulfate, how much is nitrate, how much is ammonium, for instance. And then the size distribution, we have to say how large are the particles, because the size matters. It is important for the optical properties, how they interact with radiation, how they interact with clouds, and what is the lifetime of the particles in the atmosphere. If you have coarse particles just at the end, like this big peak in the black, it's sediments like perhaps within a couple of hours. On the other side, it can be suspended for days and months. And so you won't really know how good is your model able to handle it. At the same time, you see already in this TEM image that we have some particles combined with each other. And this is what we call the mixing state. If you have individual particles separated from each other, existing individually, we call them externally mixed. But when they come together, like a core coated with some soluble particle, some soluble species, we call it coated particle or internally mixed. And here again, it matters because internally mixed aerosols and externally mixed aerosols behave totally differently in terms of optics and cloud activation or a cloud condensation on ice nuclei. One example is dust. Dust is a known ice nuclei. So it enhances ice formation. But when it is coated with sulfate, it's a cloud condensation nuclei. So you want to know that you have the right assumption when you are dealing with your ash particle or dust particle or soot particle. And morphology is another aspect that we have to take into account. But it is very difficult because then we have the dimensionality grows. So for us, morphology goes into the parameterization. In the XML files that I just showed you, in one of them, we tell the model about combination between mixing state and the size distribution. And if we assume that for each of them, we have three mixing states, let's say soluble, insoluble, and mixed. And for the size, we have 3 different modes. It gives us 9 combinations for each species. And so we have to be careful what we choose and what is physically meaningful. So theoretically, 9 combinations are there, but not all of them are physically meaningful. So, but the model is able to handle such combinations. And it's our responsibility to make sure that it's physically meaningful. So, and now I tell you a little bit why do we do model approach. Model approach is a good compromise because the size distribution is a tricky thing to deal with. The best approach is perhaps bins, having size bins, but to have a good representation of the size distribution in bins, you need at least 55 to 60 bins, and this means enormous computational effort. What we do in IconArt and any model approach, we use the log normal distribution that you see there. It basically characterizes by the size of the particles by a median diameter, dg, and the standard deviation, sigma, and the number of the particles. So if these are the 3 variables that characterize our size distribution, this means that in our equations, we have to solve 3 equations for diameter, standard deviation, and number. But these are not physical parameters. These are something that we make an assumption. What we do, we basically calculate the mass balance equations for the continuity equation for number and mass, assuming that this standard deviation is fixed, and then we can retrieve the radius. This brings us to the continuity equation for the aerosol number. In this one, on the first row, is icon. It's basically none of my business, technically. And in the second row, you see the processes like emission, deposition, sedimentation, washout, nucleation, and coagulation that contribute to the aerosol number changes. One important thing is that if we now look at the volume or mass, if you time it to the density, you see the second row appearing. And the second row are the processes that only affect mass and not the number. Does anyone know why? For instance, condensation. Why is condensation affecting only the mass and not the number? Any idea in the room?
Grows on the particles.
Exactly. You need existing particles, so the number doesn't change. It goes on the existing particle. And same is the deposition, other parameters like depositional growth or sublimation, because they always happen on the existing particles and they don't build new particles. So this is the fun of the aerosol world, and I hand over to Stefan for the fun in the chemistry world. And after that, I will be here for the questions.
Wie scroll ich jetzt weiter? Was war das Problem, Ali? Wie scroll ich weiter? Was war das Problem? Okay. Okay, so now probably a lot of you don't know me. My name is Stefan Versick from KIT. I'm one of the art gatekeepers there and working in the global modeling group. Also, meanwhile, we don't do only global modeling. Now I want to introduce you to the chemistry of art. So we just saw the continuity equation for aerosols. Now here it's the one for gases, so that's quite similar. Also here you have the icon part and then here the art part. Also different processes, again emissions, deposition, and so on. And what I want to focus on is here the chemical change. And how do you calculate this? So first I start with the detailed way. So normally you have in chemistry ordinary differential equations. As you can see here, the change in a chemical substance is production rate minus loss rate. And in most cases, those are not independent of the density, which means all the equations are coupled. So you can't solve only one equation, you have to solve several at once. And sometimes we don't want to do this because this is very computing intensive. So we are doing some simplifications. Now I want to show you what we have in art. So I start here from the left to the right, and from left to right, the model complexity within the chemistry is increasing, but also the computing time. So it's always a trade-off. If you want to do more precise, you go more to the right side of this graph. If you want to save computing time, you go more to the left. And what we have here is passive tracers, lifetime tracers, simplified tracers. I already included tracers that are based on AI. As far as I know, no one is yet in, or Ali, but very soon it will be. And then the complex chemistry, so MECA in this case. And now I go into more details for all of them. I start with the passive tracers. So passive tracers are only transported. Only transported means there's no chemical change, so this Rchem is 0. But for example, emissions would be possible, so that's how you can increase the tracer. And this tracer is useful for example, for transport studies. So for example, currently I'm working in a project where we are comparing transport processes in different models. And as we don't want any differences between the models due to chemistry, we decided to do passive tracers. In this case, we only do CO2, or mainly CO2, which has a very long lifetime, so there it's okay. If you want to do, for example, OH or something similar with a very short lifetime, this will go horribly wrong. And I also gave you an example of the XML here down for the passive tracer. So that's the one you define with CArt chem tracer. There I wanted to go back because Ali, I wanted to correct something. I only saw it now. I can't go further back. That's a new presentation. Okay. It was the slide with the nameless entries. And there was the entry CArt chem tracer, and it said for OH chemistry or something like that. That's true, but also additionally for passive tracers and other simplified tracers. So just a small correction. So in there, as I said, you define the XML file, and in this XML file, you have always the csolve, and there you define your solver for a tracer. So in this case, you just say passive, and at the top you give the tracer name. Yep. Question, does this anything? I mean, if you use, for example, molecular diffusion, it shouldn't matter. Or I mean, lower down, that's not important, but in the upper atmosphere, it would matter. Yep.
Maybe it matters. Visualize the simulation.
I think so. But definitely would matter in molecular diffusion. As I said, in the troposphere, you almost can forget about it. Okay, so then a little bit more complex lifetime tracers. The lifetime tracers have that C-solve to LT. And you set here lifetime in seconds in the XML. And then you have just an exponential decay for this tracer. So this lifetime is globally uniform. And that can be useful for very fast simulation with mainly long-lived tracers. So again, like CO2 or CH4, for example. But with this lifetime tracers, we also have some specially defined tracers. So they have a parameterized lifetime, and they are automatically applied when tracer name matches this list here. So if you define tracer that's called TRCH4, TRCO, TRCO2, TRCH3CN, or TRH2O, and define lifetime, then automatic parameterization is applied. Now just go back. That's, for example, why here, for the CO2 tracer, used a different name, that not something is automatically happening. And this parameterization, I gave you the examples. So here you can see, hope you can read it. For methane here on the left, for example, you see a height profile. Well, that's from the surface to 10 Pascal, so the top of an eigenatmosphere. And you see the lifetime here in the troposphere is more than 1,000 years and goes down to a few months in the upper stratosphere. So then we have the outcome for CO here and profile, H2O profile, and also CO2, yeah. Like, so now I have here something in front. How can I change this? So, no. So for example, for CO2 at the bottom, you have a lifetime of more than 10,000 years. And then in the upper stratosphere of a few years. Okay, not going to the next slide. No. So then we have simplified chemistry. So that, I would say, is what we use most in my group. So there are different schemes. For example, one for ozone. That's called LINOTS. And if you want to use this, then just, again, set C-solve LINOTS. And this only will work if your tracer is also called TRO3. We have some others. So for example, for simulating N2O, it's called SimNoi. Then you set C-solve SimNoi, or simplified OH chemistry, where you just set C-solve OH. This one is for calculating methane, CO. And this also is included in Julia's experiment. That one is useful for fast simulations. It's good accuracy. So for example, OH, there is a photolysis calculation in it, and that actually is quite slow, but all the others are really fast. Now I show you an example for LINOTS. So LINOTS is a linearized ozone parameterization that depends on temperature and some pre-calculated values, for example, on chlorine loading in the atmosphere. And if you then calculate this, you see here LINOTS results and here observations from NASA Ozone Watch. And so this blue hole here is just there are no observations, so ignore this difference. And as you can see here, all the structures here fit very well between simulation of a simplified scheme and the observations. Now that we also just heard a talk about climate simulations. So in the past, with icon SM1, I also did a simulation including Linots under pre-industrial conditions and 4 times CO2. And that actually also gave quite good results. So the climate change in Linots is also considered, mainly because of the temperature change we have. So then AI chemistry, well, that's not yet implemented in, at least not in official branches. So if you have access to the DKRZ GitLab, you might find some developments. There are currently several developments ongoing. So for example, OH chemistry, don't know how far that is, Ali, how close to, okay. The ozone, the paper will be submitted probably today, maybe tomorrow. So that's very close. And there's also other stuff ongoing, for example, also complete chemistry. And this one can be faster and or more complex than simplified chemistry. So for ozone, it's actually both. So it's a little bit faster and also more accurate than Linots. But you have to train a model before, which takes a lot of computing time. So that's also a trade-off. Then to the complex chemistry, well, that's one is Mecha-based. This needs then pre-processing with a Mecha/Kaba tool. This can be very complex, but it's also most accurate. But if you do there a large mechanism, this will slow down your model a lot. So I've seen slowdowns of more than a factor of 100. Well, your model simulation will be near real time if you are unlucky. And that's so it's best suited for short simulations or only local area simulations. And one example you will see in the experiment 2 by Corinna. And how this mecha is done. So there you have to define a set of simulation of gases, and that's done in a text file. And then this text file is handled by KPP, and this automatically builds then all the reactions with the rates and also does the code for the system of ODEs. Well, that's something, if you change your chemistry, you always have to run this, then files are produced, and then you have to copy them into Eigen and compile Eigen again. Well, that's it for the chemistry part directly. But also if you start a simulation, of course, you need some input data, some initial conditions. And all this input data should be put into the CArt input folder, which you find in the art name list. You have to first remap this to the eigengrid and use and convert it maybe to netCDF. And it has a special naming convention. So basically here you have always to give the eigengrid it's for within the name, and optionally the date it is for, and there's the art IO suffix, which is also given in the art name list. And here, this XXX, that defines what type of data it is. And here I show 2 types. So if you specify ICE, it's for gases. And if you specify IAE, it's for aerosols. And if you want to use this file, you have to set the IArt init gas switch to 5. And then it's read from that. But we also have other options for initialization, as the switch 0, which initializes everything with 0. 1, there are some defined climatologies in the code that are then used. And for 4, an external data set, for example, from CAMS can be used. Another topic that basically Ali already handled. So emissions. And as he already told you, we have several types of it: volcanic, biomass burning, sea salt, mineral dust, biogenic, pollen, and anthropogenic. And you can put that in different ways. For example, point sources. So there you also have to define an XML file. You define one point and then an emission rate. And I've forgotten which experiment that was. I think, okay, also in Julia's. We will learn how to do this. Then for sea salt, no extra data is necessary. For mineral dust, you define this art STY, so than before. And for biogenic, anthropogenic, and biomass burning, you also can define these abbreviations.